And basically, we have 3 other carrier speakers today, and Rebecca is one of those.
All right. Thank you for having me. Today, I'm going to be giving a quick talk about Antarctic contributions to sea level and what we're seeing in our satellite gravity models. I'm going to spend the first half of the talk basically going through some comparisons of the gravity models we produce at the Australian National University with some other popular models, and then spend the second half of the talk actually looking at what that's telling us about Antarctic contributions to sea level. So just quickly to give you some background on the GRACE and GRACE follow-on missions. They're basically 2 missions that occurred from March 2002 to October 2017. Bit of a gap between the initial GRACE mission and the GRACE follow-on mission, which was launched back in May 2018 and is still in orbit today. The concept of the missions basically that you have 2 twin satellites that fly around the Earth following each other, and they measure super precisely the distance between those 2 satellites. And within those measurements is information about how mass is changing on the surface of the Earth, plus a whole bunch of other stuff. Basically, we need really accurate background models to be able to isolate those changes that are being induced by things like surface mass balance. So the pros of these missions are that it's basically the only direct measurement we have of mass balance on a global and spatially continuous scale. Although there are also some cons associated, which includes things like relatively low spatial resolution, especially when considering the high spatial resolution we get from satellite altimetry. We're also really sensitive to glacial isostatic adjustment, which we know could be more accurate. Okay, so just so you understand basically what I'm going to go through here, I'm going to describe briefly the processing steps that we have to go through to actually generate mass balance models from the GRACE and GRACE follow-on data. What we have to do is we have to model the orbits, integrating all of the different accelerations that we know are acting on the satellites, and we're left over then with the orbit perturbations that are caused by those changes in water masses as they move around the surface of the Earth. So we then are able to invert for the temporal gravity field, and we can use something called mass concentration elements to parameterize the temporal gravity field, or we can use spherical harmonic coefficients. In this talk, I'm going to be comparing 4 solutions, all of which use mass cons. So I have there the CSR solution, which is from the Center for Space Research at the University of Texas at Austin. I've got the JPL solution, the Goddard Space Flight Center solution, and our ANU Release 2 solution, which is not yet publicly available, but will be very, very shortly. And what you can see from these figures up here is that we all sort of roughly produce a similar pattern of mass change estimates. There are some obvious differences in the way that we sort of parameterize our temporal gravity field. So you can see our solution, for example, is quite blocky with these irregular shapes, which are just the irregular shapes of our mass cons, whereas the JPL solutions are higher, they're larger mass cons still. Some are more smooth than others. So these choices that we make for how to parameterize the gravity field is important for knowing how those decisions change the spatial patterns of our solutions. So we know that we've got this signal in the CAMB ice stream where we have significant mass gain, which is flanked by mass loss where the Mercer ice stream, upstream of the Mercer ice stream, which we can see in satellite altimetry. What you can see here with the comparison of the 4 solutions that I just described earlier is that some of those solutions aren't able to resolve those highly localized signals. That's due to things like how we constrain our solutions. So some, for example, Goddard, they use spatial and temporal constraints on their solutions, which causes some smoothing, whereas our solutions, we try to reduce the need to use those constraints as much as possible. And what we end up with is being able to resolve as well as we can with the size of the mass cons that we use, the spatial pattern of CAM ice stream mass gain. So we also all have to define our coastlines a specific way. We all do that slightly differently. For example, the CSR solutions, they include ice sheets in what they define as being land. And this is important because we all also constrain our solutions by ensuring that there's a conservation of mass between the land and the ocean, such that if there is mass gain on the land, then there is mass loss in the ocean of an equal magnitude. So when we use our center-defined coastlines, what we end up with is an integrated mass change pattern in, the Antarctic ice sheet. We all sort of roughly plot on top of each other, so we're getting similar results here. But if you pull out the West Antarctic ice sheet, you can see there's a bit of spread between the four solutions. What's important here is that if we use a consistent coastline, we end up agreeing much more closely. And you can see that in these differences here. So the largest differences are for the Centre for Space Research Solutions, which makes sense because what they define as being Antarctic ice sheet is a much larger area than the other solutions. So onto some actual results to show what's happening in Antarctica and what that means for modern day sea level rise. What I've done here is just integrated, before I go to that, what I've done between this slide and the next slide is created a combined mass con solution for these four centres to create basically just an average solution. It's a little bit more complicated than that, but not that much. And I will be showing those results here. So the combined four-centre solution, what we get is significant mass gain in East Antarctica to the tune of 46 gigatons per year. We get mass loss of 155 gigatons per year in the West Antarctic and minus 23.7 gigatons per year in the Antarctic Peninsula, which all works out to mass loss of about 132 gigatons per year. What's important at this point to note is that satellite gravity models, we all tend to roughly agree with each other in terms of these magnitudes of mass loss and mass gain on the Antarctic ice sheet. But when we have a look at other methods that are available to us to make these mass balance estimates, such as altimetry and the input-output method, for example, I'm just pulling out results here from the most recent MB3 assessment. What you can see is that while the GRACE follow-on satellite gravimetry results work out to be something quite similar to what we've produced here, we get the complete opposite estimate from the input-output method and a much lesser magnitude of mass gain from satellite altimetry. These are the rates over the intercomparison period, so 2002 to 2019, from the combined solution that I've produced here. And what you'll see is that for the East Antarctic ice sheet, we agree really well with what MB3 has produced as the combined gravimetry solution. So breaking that up into separate basins, you can see that the majority of the East Antarctic ice sheet is gaining mass, with the exception of some basins in Wilkes Land. And you'll also see that the majority of mass loss that's happening not only in West Antarctica, but for the whole ice sheet is being contributed by Basin 11 there. So for those who would prefer to see that in terms of millimetres of sea level, this is the number of millimetres of sea level contributed from each basin over a 20-year period from 2003 to 2023. And in terms of percentages, that ends up being about 20% of ocean mass gain over this period contributed from Antarctica to modern sea level rise. That's not total sea level rise. You can basically halve that if you want to consider thermal expansion. And what you can see is the majority of that is obviously coming from the West Antarctic ice sheet, while the East Antarctic ice sheet is attenuating that a little bit by pulling 6.5% equivalent sea level from the ocean. And you can see as well, Basin 11 contributing the majority of that mass loss into sea level rise. So just pointing out here some changes in trends across the West Antarctic time series and East Antarctic time series and the Antarctic time series, and you can see there's some significant changes in trend across the Grace and Grace follow-on period. What I want to point out specifically is what's happening in East Antarctica. We've got this massive increase of 206 gigatons per year occurring from 2020 until present. We've also got a significant slowing in the Antarctic ice sheet of mass loss, which is coming a little bit from East Antarctic ice sheet, but also the fact that the West Antarctic ice sheet mass loss has decelerated over a similar period. And just to finish up, I'm going to flick through these slides to show you going from this basin up here clockwise to have a look at the detrended mass gain or mass loss in East Antarctica. The yellow bars show significant periods where there were extreme weather events associated with atmospheric rivers that dumped a bunch of snowfall on the continent. And you can see as I flick around, looking at these detrended time series, that once we sort of get around to Wilkes Land here in this sector, we start seeing significant mass gain from around 2020. And some of that mass gain is coincident with the large atmospheric river we saw in March of 2022. So I'm out of time, so I will leave the summary up here. Yeah, thank you.
Thanks, Rebecca. Yeah, we've got to move on to the next talk. So if you have questions for Rebecca, please track her down at the coffee break. Our next speaker is Heiko.